Hello, everyone. Welcome to my talk. My name is Pau, and I'm here to talk about how to build an augmented reality application with Compose and OpenGL. Hope you all have had a lot of fun and learned a lot in these 2 days of DroidCon New York, and hope you're ready for one last session. Quick thing before we start. The thing that motivated this talk for me to make this talk was that I've seen throughout my years of working with AR, people were asking things like, how do I render something with AR Core? How do I render, I don't know, a line with AR Core? So it was always with AR Core. And so I realized that somehow many people didn't understand the separation between what AR Core does and the actual rendering. And so now that we have Compose also, I thought it was a good opportunity to see how we can combine the three: Compose, OpenGL, and AR Core. So we'll explore different techniques that we have for 3D rendering, and we'll see how an augmented reality experience is not that different than any other virtual experience. Quick disclaimer before we start. This talk is purely for educational purposes, so I'm not here to sell you any type of rendering engine or specific framework. So everything I'm gonna say are concepts of purely OpenGL. Then I have prepared a sample project. It's available on GitHub. I will show the link at the end. And yeah, you feel free to take that code in your application. Just be aware that code might not be production ready, so test it beforehand. Also, I'm going to be focusing a lot on AR experiences using the rear camera, so AR on the real world in front of you instead of applying filters on your own face. And yeah, last but not least, you probably know that on Android we use the OpenGL ES, the embedded systems version of OpenGL. But for the sake of simplicity, I'm just going to say OpenGL throughout. OK, let's start. How do we render OpenGL content when using Compose? Well, we can't do that directly. We still have to use traditional UI toolkit. We still have to use the surface that the Android UI framework gives us. And we have to do it through the surface view or the texture view. With these two classes, we only get the surface, and we have to use the EGL library to create the EGL context and the EGL surface. That's a bit low level. And then on top of that, you have to handle your own render thread. You can render on the main thread, but it's usually not recommended. You probably know that we also have the GL surface view since API level 3. That does exactly that. It creates the EGL context, EGL surface, and it has a render thread for us. If you want to do Vulkan, then you have to work directly with the surface and either surface view or texture view. But if you're going to do only OpenGL, probably you're better off with the GL surface view. So from Compose, we're going to be using still one of those. And thankfully, the engineers at Compose created the Android view, where we can integrate any traditional UI toolkit view. So we can build, on top of that, our custom composable, and we can wrap any of those three. As I was preparing the slides some months ago for DroidCon Berlin, I saw that in Compose Foundation 1.6, they released these two composables, Android external surface and Android embedded external surface. We'll see the source code in a second, but I can already tell you that they do exactly that. Both of them use an Android view to end up using a surface view and a texture view. So everything at the end boils down to using one of these two, and we have to understand a bit the differences. With the surface view, which was available since the very beginning, the way it works is that the system creates a hole in the view hierarchy, and the OpenGL content is placed either behind or in front. So that didn't solve some of the use cases, and that's why they introduced the texture view in API level 14. And some of these use cases were wanting to place OpenGL content in between other view elements. And the way they accomplished that was that it copies the OpenGL content into the view hierarchy. This extra copy also comes with a cost in performance, and Google recommends using the surface view if you can. Only if you know that you're going to be placing the OpenGL content between other views, then it's recommended to use the texture view. Otherwise, it's better to just stick with the surface view. That's my cue to go to the sample project and see some code. Is it big enough? So here's my implementation of this custom composable, called it OpenGL view. And internally, I'm using this Android view to create, in this case, a GL surface view. And if you have ever worked with GL surface view, you're probably familiar with the calls to set EGL context factory, set EGL chooser, set the EGL config chooser, and finally set render. I've done a couple of things around the whole thing to handle the lifecycle correctly, but shouldn't be too complex. Let's see. On on Compose Foundation, the two composables I mentioned, Android external surface, that's exactly the same, using an Android view to create, in this case, a surface view. And down here, we have the Android embedded external surface, which uses an Android view to create, in this case, a texture view. All these differences between surface view and texture view are also documented up here in Compose Foundation, so feel free to read through that, and you will also realize that they recommend using the version that uses surface view as much as you can. So for the rest of the project, I stuck with my custom composable because I already had it implemented, so it was just easier to work on top of it. Using that should be very straightforward. As any other composable, we can integrate this OpenGL view composable within other composables. In this case, I created a render here, and I made it full screen. The renderer, which is defined down here, it's only changing the background color every frame. Nothing too exciting yet, but should give us a hint of how to do it. You can see here in the preview, the GL content is gray, and that's, of course, because the Android Studio, the preview in Android Studio doesn't know what the OpenGL content is going to be. So we can hide now the preview and open my running device. I have it here with the sample, and if I execute the sample, we can see exactly that. So that's the code on the left running on the device. Full screen OpenGL content through Compose with the background color just changing. Let's go back to the slides, because now that we know how to integrate Compose with OpenGL, or OpenGL with Compose, wanted to explain a little bit about OpenGL. I'm not going to go into very detail. It's not a full course. It's a crash course. I hope to clarify things that are sometimes misunderstood or are a bit confusing maybe for some people. But if you want to learn more about OpenGL, come to me afterwards. I can provide you a few links. First thing, OpenGL itself is just an API, and it's an API of rasterizer. And what that really means is that the main job of the rasterizer is to convert 3D data into a 2D representation, into an image, and that's what's going to be on the display. I'm going to be talking a lot about 3D data and transforming this 3D data, because OpenGL itself doesn't have concepts of 3D model or 3D mesh, virtual world, virtual camera. All these things are known to OpenGL, and we have to, using the OpenGL, we have to process that data to accomplish what we want. So this process of converting the 3D data to a 2D representation is done with the graphics pipeline, which is a series of very well-defined stages. And some of these stages we have to configure, we have to provide the code that will be executed on the GPU to accomplish that. That code that runs on the GPU, these programs are called shaders. Probably you've heard of shaders before. And at the end of the day, what we want from the CPU is to send some commands, right, and end up seeing something on the display. And every time we send one of these drawing commands, we go through the graphics pipeline. This is a simplified version of the graphics pipeline.
And it goes something like this. First, we send that 3D data, vertex data, and data associated with each vertex. And first, there's the vertex shader that we have. This is one of the stages that we have to configure. And the vertex shader is executed in parallel for every vertex. And the goal is to transform all of these 3D data into the coordinate system that OpenGL expects. I'll get back to that in a sec. Then there's shape assembly and the geometry shader, which combined are in charge of generating those triangles out of the vertices. And then there's the rasterization step. This rasterization is the process of dividing each triangle into different fragments. You can think of fragments as pixels, but they're not exactly the same. There isn't a relationship one-to-one. Sometimes we have more fragments than pixels on the display, sometimes less, depends on the situation. Then there's the fragment shader, which, similar to the vertex shader, is also executed in parallel for every fragment in this case. And the goal of the fragment shader is to output the color of each fragment. There are some tests and blending operations executed on the GPU, and finally all of that goes to the output, which is the color buffer. It doesn't go directly to the display. It goes to this buffer, which belongs to a frame buffer. I'll go back to frame buffers later. And only at the very end, the content would go on the display. So from the graphics pipeline, I want to focus now on the vertex shader, because as I said, we have to transform all this 3D data into the coordinate systems that OpenGL expects. And that coordinate system is what's called clip space, also normalized device coordinates, NDC. They're technically not the same, but for practical use cases, it's usually, you can consider them the same. Actually, some documentation I read today, documentation from Apple, they say it's the same, even though it is not. But I won't go into details there. So in the vertex shader, we have to transform all the 3D data from our 3D models, all the vertices that we get placed on somewhere in the virtual world combined with the virtual camera. We need to transform it into clip space. And this clip space, this cube, it goes from -1 to +1. And the goal of this is that every piece of geometry that is outside of this cube is clipped, and then it's discarded, doesn't continue further in the graphics pipeline, and therefore those 3D elements won't be shown on the display. Only the things that are within the cube, this clip space, then continue in the graphics pipeline and will continue and finally end up on the display. So with that, and working with the OpenGL API, one would typically build some type of rendering engine, would have an easy way to render objects, usually with textures, of course, and then would have a virtual camera class, which would contain a view matrix and a projection matrix, and then some type of scene graph can be very simple or a very complex graph. Let's go back to the sample project, where I have here this other sample, which illustrates a bit that. I have, again, this OpenGL view with a different render in this case, and I have these composable arrow controls on top of it. Now in the preview, we can see those arrows, but not the OpenGL content, again, because of the same reason. And here is one very simplified scene graph, just a list of hard-coded elements at hard-coded positions. Down here, I have all the different functions to control the virtual camera and be able to navigate the virtual world through those buttons. So this would be this virtual scene with the arrow controls that we can use to navigate this virtual scene, a very exciting virtual scene. If you like cats like me, then you probably like this. So we're now a step further from what we had before. But probably you're asking yourself, hey, I came here to hear about augmented reality. What is all of this? So let's go from virtual to augmented reality. With augmented reality, what we want is to augment the reality, right? So in order to augment reality, we need to see that reality. We need to see the real world. We need to see the image that we get from the camera. And so let's see how we could render the camera image. To render the camera image, we need to get, of course, the data from the camera sensor. And then in order to render anything, we still need to go through the graphics pipeline. So we need to submit some 3D data to OpenGL. And this is one of the cases where we don't need to use a virtual camera place 3D geometry in a virtual world. We can directly have our geometry in clip space. We can define a plane or quad in NDC coordinates, so from -1 to +1, and that will ensure that our image will occupy the whole view. So that, and working with texture coordinates, we can then sample the image from the camera sensor and render our camera image. Let's go back to the sample code here. In this one, I have now, again, just OpenGL view on top of it, camera permissions composable, should be straightforward. And down here in the render function, I first clean the screen, and then render the camera image, and on top of it, I render the virtual scene. To render the camera image, I have this utility class that handles ARCore, but you can see here, these are the coordinates for that 2D quad in NDC coordinates from -1 to +1, and then we get the texture coordinates from ARCore. If you were to work with another camera API, be it Camera 2 or Camera X, doing your own rendering, you have to handle the transformation from the camera sensor, the orientation of that one relative to your device. With ARCore, that's already handled for us. We just call that function, and we get the corresponding camera coordinates. So let's see that now on the device. And we have now our virtual scene placed on top of the camera image. So now we are getting closer to that augmenting reality. And the question would be, is this AR though? How many of you do you think this is AR? Okay, one hand. I'm sure many people would argue that this is not AR yet, because we're not augmenting anything, right? We're not using any context from the real world. We just have a background image, which happens to be the camera image, and something on top of it. On the left-hand side, we had those arrows, where I was able to control the virtual camera to navigate my virtual scene. On the right-hand side, I don't have those arrows. I cannot control the camera, the virtual camera. And adding those arrows there wouldn't make much sense anyway. So we need to find a way to be able to navigate the virtual scene in the same way that the real-world device is moving. And that's where ARCore comes into play, because ARCore has two main responsibilities, which is tracking the position of the mobile as it moves, and it also builds its understanding of the real world. So let's focus on the first part, tracking the position of the mobile as it moves. ARCore knows the relative position as it's moving around and orientation, so we could use that data and update our virtual camera to be able to navigate that virtual world. So if we do exactly that, if we get that data from ARCore and then update our virtual camera, we should be able to see that we're navigating the virtual world with the same movement. If I go back to the same sample, up here where I had the update function and ARCore is updated, let me rebuild the project. Down here, this function should be very easy and straightforward to follow. As I said, I get the camera object from ARCore, and then just get both matrices, the view matrix and the projection matrix, and set it to our virtual camera. So from what we had 1 minute ago, just background image and some virtual scene on top of it, now we have this. Only with this little change, now our virtual scene is not anymore somehow just something placed on top of it. It's part of this virtual world. But still, with that, I like to think of this as still just a background image and a virtual scene on top of it, because that's what it is, right? We've seen that we're only updating that virtual camera data, and with that, we accomplish that. So if there's one thing that you're going to remember from this talk, I hope it's this one. From a rendering point of view, this is just that, a virtual scene that has a background image, and the virtual camera is updated with the same movement as the real world device is moving. Maybe some of you are thinking, yeah, that's obvious. I think it's very powerful to think of it that way, because there are many frameworks nowadays that try to enforce things like always rendering full screen the AR experience. You don't necessarily need to do that. So let's move on. With AR Core, we also have this environmental understanding. And as AR Core is navigating the world, it's looking for things they can track. It's looking for trackables. It starts by detecting different distinctive points in the scene that they can track frame over frame. And then from feature points, they also create planes. And as AR Core is improving its understanding, the virtual world coordinates might change. And that's very important also among different AR sessions. If you start an AR session facing this way, the world coordinates are going to face in this direction. And if you start now an AR session facing that way, the world coordinates now are facing in that direction. So it's not recommended to just place things at the hard-coded position because they might not be where you expect them. And also, as AR Core is improving its understanding, this world origin might just jump around. If you start a session and then kind of put the device down maybe for some minutes, and then you put it up again, that world origin might change. So if we want to put things, we want to place things attached to real-world objects, we have to use anchors. And anchors are the way to tell AR Core, please remember this physical location. I want to keep virtual elements next to that physical location. In order to create anchors, we have to use the AR Core session class or object, and we can do it through a heat test where AR Core will do a raycast, and then we get those trackables. We can get the feature points and planes where we can attach our virtual objects. Fast forward to more advanced topics. Back in 2020, AR Core released the Depth API. And it said, Depth API understands the size and shape of real objects in a scene. It creates depth images or depth maps, thereby adding a layer of realism into your apps. This first part here understands the size and shape of real objects in a scene. It's very powerful because now instead of just feature points and planes, we also get depth points. And the depth points, they tell us the depth from the camera sensor to the real-world object. And they're actually more accurate. They tend to be more accurate than the previous feature points, from my experience. And this second part creates depth images or depth maps. Google, when they released it, they showed these two examples. You can see on the left-hand side, this hallway with the bike, and next to it, the depth map. Each color in that depth map represents different distance from the camera to the real-world object. And that is an image, it looks kind of cool, but it's probably not so useful for users on its own. So on the right side, you can see one way we can use that depth map. So on the right side, you can see the virtual CAD that is on the left side without occlusion, and on the right side with occlusion. Occlusion means the virtual object is hidden behind the real-world object. And the way this works, it's very straightforward. because we have the depth map. We know the distance per pixel to the real-world object. And we also know we're in full control of our virtual scene, right? So we also know the distance per fragment or per pixel to our virtual objects. So if it happens that the real-world object is, I don't know, 5 meters away, or feet, whatever that is in feet, and then our virtual object happens to be farther away, let's say 10 meters, in the fragment shader, we can compare those distances. And in each fragment, we can decide to discard them, and therefore they won't be rendered. And that's the way we can create occlusion. For each fragment, we decide whether we show it or not, and we can hide virtual objects behind real-world objects. Again, remember that this is still a background image with a virtual scene on top of it. Last year, ARCore released electronic image stabilization, which helps to reduce camera shake in videos. It works by detecting small movements in the camera and then compensating for them by shifting the image being displayed. Shifting the image being displayed. When I read that, I thought, well, I know how to render the camera image. I have a 2D quad in clip space, and then I asked ARCore for the texture coordinates. So I thought, maybe this shifting has to be something like they will just adjust the texture coordinates to create that image stabilization. Turns out it's a bit more complicated than that. And now instead of using a 2D quad, we have to use a 3D quad. So quad defining 3D coordinates, and that shifting, it's this quad being tilted in one direction or another direction, depending on how the device moves. So that, on top of handling the camera sensor orientation to create occlusion for each individual virtual object, I thought it was a bit cumbersome, and I thought, maybe there's a way I can simplify this process. Maybe I can convert this 3D quad back to a 2D quad. And if you think about that, it's exactly what the graphics pipeline does, right? We convert 3D data back to 2D data. So how can we accomplish that? Let me introduce you to frame buffers, our advanced section of the OpenGL crash course. If you remember frame buffers from when I explained the graphics pipeline, the Kronos website defines the frame buffer as a collection of buffers that can be used as the destination for rendering. And there are two kinds, the default frame buffer and user-created frame buffers called FBOs. This default frame buffer is what the system or the framework creates for us, so it's usually the display. And then the rest of the explanation somehow already tells us that we, as users of OpenGL, we can create frame buffers, and we can use them as destination for rendering. For the sake of completeness, frame buffer is a collection of buffers, which are the color buffer, the depth buffer, and the stencil buffer. As I said earlier, what we want usually is from the CPU to send some rendering commands and see something on the display. But now that we have frame buffers and we can use them as destination for rendering, we're not rendering on the display anymore directly. We're rendering somewhere else on a frame buffer. And we can render our virtual scene there. We can also render our scene from a different point of view, maybe apply a different effect. And we can have as many frame buffers as we want. Note also that I draw them with different sizes and shapes. Frame buffers can have any size that you want. And what's very powerful of this is that we can later on use that information that we've rendered somewhere else. When we render on a frame buffer, we render on that color buffer, which is usually a texture, and we can use those textures somewhere else. So now we could, for instance, render our 3D scene using the information from those textures, from those two frame buffers, and maybe create a scene with dynamic shadows and apply some post-processing effects, for instance. So let's go back to where we were with depth API, image stabilization, and frame buffers in order to simplify that 3D quad back to a 2D quad. Now we could start rendering our virtual scene on a virtual or frame buffer that I called virtual scene. Then we can also render the depth map, and here compensating already for all the image stabilization transformation, and we transform from that 3D quad back to a 2D quad, which is our texture. Then later on, we render the camera image onto the default frame buffer, and finally, last render step, we combine those two textures to render our virtual scene on top of the camera image using or applying occlusion using that already simplified depth map. Note at this point, there's nothing on the display yet, only at the very end with the framework does the swap buffers call, only then things are put on the display. Let's go back to our sample project. And in this one, I have implemented exactly this process. Again, it's an example of how to implement all of this. We have a first render pass, rendering our virtual scene on a virtual frame buffer that I call virtual scene. Then second render pass, if we have depth data, then we render that raw depth data onto this texture. And this is, at this step is where I'm converting from that 3D quad back to a 2D quad because it's going to be rendered on a texture. And then finally, on the default frame buffer, which is going to be the display at the end, clear the screen, then render the camera image, and on top of it, combining those two frame buffers or the textures attached to them to render our virtual scene with occlusion. And we can see that in action. Okay. So now, scan the scene properly. We can place a couple of objects here. We can see how they are correctly occluded by podium. You can also place another maybe more interesting 3D object. Probably you can see there that my hands are shaking a bit, so I can enable image stabilization, and that should make the video much more stable. Can also render the depth map, which should show you, all of you with the depth map. Yeah, and so we started with a very simple sample, just changing the background color, and we ended up with something much more complex and not the many steps. I didn't want to leave this without mentioning the OpenXR standard. Probably you've heard of it. It's used also in web. If you've heard of WebXR, it's using the OpenXR standard. And also in virtual reality headsets such as the MetaQuest. They're using the OpenXR standard. It works slightly different than all of these that I have explained. Well, the techniques are the same, except that the framework doesn't allow you to get the camera image. They say it's because of privacy reasons. And so the way it works is that the application has to render the virtual scene on frame buffers, and then it gives those frame buffers to OpenXR, and it tells you how it needs to composite the whole thing, showing the camera image or not. So final recap, we've seen how to combine Compose and OpenGL. We have created a custom composable using an Android view, and we have also seen how Compose Foundation provides us with Android external surface and Android embedded external surface. And we've seen the difference between surface view and texture view. And still that with those we have to render, we have to handle the AGL context and the AGL surface, and we have to handle our render thread as well. And prefer using surface view before instead of a texture view if you can. And on the right side, we've learned how AR Core doesn't do any of the rendering. AR Core does all the heavy lifting actually,
and provides us with data to render that AR experience. We've used OpenGL to render the AR experience, and we've seen that it's not that different than any other virtual experience. And we've also explored some advanced topics, such as frame buffers, to do some off-screen rendering and use that information at a later step in our application. So with that, I would like to thank you all for coming to my talk. Here are the links to the GitHub repo and to my LinkedIn and X handler. And if you have 5 or 10 seconds, I would really appreciate if you could scan that QR code and give feedback on this talk. It will help me a lot. So yeah, thank you all for coming, and I will take any questions.